on top. B indicates the magnetic field. If you inject protons over here, they make circles because they are charged particles. They make circles in a magnetic field, so they go around. But each time they come by, you hit them with a little negative electric energy, and that, of course, makes them go faster because they're positively charged. If they go faster, they go in a bigger circle. And you keep doing that until they come out at much higher energy. So this is just a machine for making high energy. We don't need to worry about how it works. Eventually, in the beginning, he was all for the use of plutonium for a bomb project because he did not understand or did not believe you could separate the isotopes of U-235 from uranium-238. But eventually he came to realize that this machine, his machine, would separate these things, and that made a big difference. His ideal situation was to have a goal in mind. The analogy of a bull in a china shop is not unlike Ernest Lawrence. I spent the first few years of my graduate education working at Cal Berkeley on the biggest machine he ever built, and on a very peaceful experiment. Had nothing to do with weapons. And it was a wonderful time, especially the girls in California were very nice. A physicist from Harvard, Kenneth Bainbridge, went to Britain to help with radar work. But Bainbridge had also worked in nuclear physics, and so he was invited to sit in with the Maud Committee. You remember the Maud Committee was the committee that G.P. Thompson had formed that had all these Nobel laureates, British Nobel laureates on it. And he too was stunned at the progress that the British had made. And this is what he wrote. They knew what to do. 3 years, and you could have a bomb. The U.S., of course, was not in the war in early 1941, but it was clear to everyone that war was coming. Now, the U.S. is a big country, of course, with big resources and much bigger and stronger than Germany or the United Kingdom. And I like to give the analogy of it as a large physical object. Big physical objects have a lot of inertia. It takes a lot of force, energy to get them moving. Once they're moving, they have a lot of momentum. And this was very true about the United States. Extra urgency was added to all the efforts in all countries on June 22nd in 1941, when Hitler launched Operation Barbarossa and invaded the Soviet Union. During this time, Segre and Seaborg in Berkeley had isolated enough of this new element, plutonium, to test out its fission possibilities, which turned out to be very high. In fact, they are higher than uranium-235. And every country in the world who can make plutonium does make it for nuclear weapons. Now, it's better, as it were. In the meantime, the U.S. learned from the Maud Committee that separating the isotopes really did look possible. By July of 1941, the British sent a report with these three conclusions. They sent this to the United States, and it could be decisive in the war, and it continued, and we should continue the British in collaboration. Both Bush and Conant, who were had contact with the United Kingdom, understood that a major push from the U.S. Was a necessary thing to do. In Germany, meanwhile, work continued. And I want to just add a story about one of the most amazing human beings I know of. He was a strong anti-Nazi who eventually was forced to work for the German war effort, of course, very reluctantly. The pressure on him, as we will see, was considerable and obvious. His name was Fritz Houtermans. I don't know if any of you have ever heard of Fritz Houtermans. He was a great genius. He had a Jewish mother, and he was a long-time member of the German Communist Party. In the 1920s, while he was working at Göttingen, he's the first person on Earth to figure out what made the sun shine, the fusion reaction that works inside the sun. And the story is told about him that he was out walking one night with his girlfriend Charlotte Riefenstahl, who was not in any way related to the Nazi propagandist Leni Riefenstahl, but she was his first and third of his 4 wives. And it happens. So they're walking hand in hand. She looks up and looks at the stars and says, "Oh, how beautiful the stars are." And his reply is, "Yes, and you were holding hands with the only man on earth who knows what makes them shine." They were married and emigrated to the Soviet Union in 1933 when Hitler became chancellor. However, he fell into disrepute in one of Stalin's purges and was arrested and refused to talk and give any information about anything he knew because his wife and new child, he was hoping they would escape, which they managed to do, and got to Denmark and then to the United States, which he did not know. So he refused to talk. Meanwhile, he was tortured, all of his teeth were knocked out, and he was put into solitary confinement for months on end. While he was in solitary confinement to maintain his sanity, he solved math problems in his head. And he solved one of the significant maths problems in his head that was outstanding at the time, and he wrote it down on pieces of soap with the end of burnt matchsticks. It's just a remarkable man. Well, then in 1939, there was the Molotov and Ribbentrop Pact and peace, so-called, between the Soviet Union and Germany. So the Soviets handed him back to the Germans. And he would normally have been killed pretty quickly, but he was protected by Max von Laue, who was a strong enough anti-Nazi and a Nobel laureate to withstand Nazi pressure. And so Houtermans was forced into working for them. By August of 1941, he knew how to make atomic bombs. Okay, but because he was a very strong anti-Nazi and he had learned to keep his mouth shut despite the lack of teeth, he did not reveal any of that stuff. He was also a heavy smoker, and so he would requisition tobacco, even though it was very heavily rationed during the war in Germany. And his excuse was that he needed it for heavy water research. And that worked for a while. And then he was found out again, and this time he was protected by Werner Heisenberg. So he had a very impish sense of humor and was terribly proud of his Jewish heritage. And he liked to say, quoted as responding to Nazi anti-Semitic remarks, saying, "When your ancestors were still living in trees, mine were already forging checks." But on a trip to Zurich, Switzerland, to go to a meeting, he sent a telegram to Eugene Wigner in the US saying, "Hurry up, we are on the track." In the UK, meanwhile, Churchill's science advisor, Lord Cherwell, sent the following message to him. 10-to-1 on success within 2 years. Well, took a little bit longer, but it did work. The crucial the crucial push to get the Americans moving came actually from Mark Oliphant, the head of physics at Birmingham, to whom I've referred a few times. He flew to the US in August 41. He visited Lyman Briggs, the head of this uranium committee, only to learn that what he called this inarticulate and unimpressive man had put the Maud Committee report, which had been sent to him, in his safe and had not shown it to any members of his committee. That action delayed the bomb by 6 to 8 months, meaning that it could not be used to end the war in Germany, and probably cost the lives of tens of thousands of people. In late 1944, when the bomb could have been ready, Hitler was in a bunker in East Prussia, far from any civilians. And had the bomb been dropped on that bunker at that time, the war would have been over 8 months before it actually was. Oliphant then went on to Chicago, and he spoke with Samuel Allison, who was on this Lyman's committee, and who had, of course, no idea, and was shocked that a bomb was possible because he thought they were working on a propulsion system for submarines. Then Oliphant flew out to Berkeley to talk to Ernest Lawrence, because he knew that Lawrence was a dynamic person. Lawrence showed him his ideas for using the cyclotron to separate ions. And he arranged for Oliphant to meet Bush and Conant. And Oliphant gave them a summary of the Maud Committee report, which was quite long. He also spoke with Fermi, and he had meetings with the National Academy of Sciences. Then Bush and Conant then wrote, the chain reaction would take place through the direct action of fast neutrons, the original idea of Otto Frisch. This information, so far as I know, was not available in this country till after the National Academy of Sciences had sent in its second report. I think it should be given serious consideration. And of course, the information had been available. It was locked in Lyman Briggs' safe. Now, as an aside, there was a conversation at the time between Fermi and Edward Teller, September 1941. Fermi made a throwaway remark. He wondered, a fission bomb creates an incredible amount of energy, a huge temperature, and therefore high moving protons. Would it make enough heat to make the protons move fast enough so two protons could get really close together despite the fact that they're electrically repelled? If they could get close enough together, then the strong force between them would take over and bind them together and turn two hydrogens into helium. And the mass of helium is less than the mass of two protons. And the difference is energy from E equals mc squared. This is the largest source of energy in the universe, just about, and what makes the sun and stars shine. In stars, the protons are crushed together, but they're crushed together by the immense gravitational forces. If you think of the size of the sun as a sphere, the Earth is a dot on it that you can barely see. That's how big the sun is. So the gravitational forces are huge. Now, this remark was not serious on Fermi's part, but it made a huge impression on Teller, and one which would have near-term and long-term consequences, and eventually would lead to a fusion bomb or the hydrogen bomb in the early 50s. A bomb which is per atom anywhere between 7 and 9 times more energy than a fission bomb. However, a fission bomb is limited in size to somewhat around 1 million tons of TNT. And that's because the energy of it blows it apart, and the fission stops because the atoms are so far apart. So you can't make them bigger. A hydrogen bomb, which maybe if I can bear this subject anymore, I'd talk about next year, it is unlimited in size. You put more stuff in, you get a bigger bang. The largest bomb ever, I just mentioned in the film, which I saw on when I was working on non-proliferation problems in Russia, the largest bomb ever built was built by the Russians. It was equivalent to 50 million tons of TNT. And I calculated that for those of you who know anything about London, it would kill every human being within the M25 circle and destroy all the buildings. I mean, that's a big bomb. Anyway, the Maud Committee report was eventually transmitted to Conant on the 3rd of January, and this is all 41, and on the 9th, Bush carried this report directly to the president, and he presented it to Roosevelt and Roosevelt's vice president, who at the time was Henry Wallace, and that 25 pounds, or about 11 kilograms of uranium, might explode with the equivalent force of about 18,000 tons of TNT. That the uranium could come from Canada or from the Congo, that a vast industrial plant would be needed to separate out the isotopes of uranium, something which would cost several times the cost of a major oil refinery, that the British estimated that the first bombs could be ready by the end of 1944, and that a plant could produce no more than 2 to 3 bombs a month. And he based all of this on laboratory investigations and could not guarantee a positive result. Roosevelt formed yet another committee, this time with himself, with Henry Wallace, with Henry Stimson, the Secretary of War at the time, whom I will talk about later, George Marshall, the head of the Army, who is responsible, of course, for the Marshall Plan after the war, and with Bush and Conant. You notice there are no physicists and only one chemist on that. Scientists were out of the question in terms of using the bomb. You could work on the project or not work on the project. There's a lot of discussion, which we'll have on Friday and Saturday, about whether scientists have any more right to discuss the ethical problems of use of this or not. Given that most people knew what the Nazis were capable of and the quality of Nazi scientists, most people were quite keen to join. Arthur Compton at Chicago was now the scientific head of the project. Bush and Conant went to him for yet another review of the situation, and it was suggested that Conant talk to Fermi, which he did, and he went east to talk to Fermi, who worked out on the blackboard that the amount of fissionable material needed for a bomb, the most conservative calculation was somewhere between 50 and 100 kilos. That's not much because it's very dense stuff. And of course, the problem was separating isotopes. Harold Urey, who was a chemist also at Columbia and had won the Nobel Prize in Chemistry for the discovery of deuterium, the isotope of hydrogen, was called on to discuss the separation of isotopes. And he pointed out, as I've mentioned before, that you cannot do this chemically. And what he wanted to do was build a centrifuge, because if you have a centrifuge spinning around, that heavy elements go out to the edges and light elements stay in the middle, and you can do that. And that is currently the best technique that everybody uses right now to separate uranium isotopes. The problem with that is that the technology was beyond 1941, because the speed with which these things have to revolve is enormous. And he estimated that it would take 40 to 50,000 centrifuges. That's a long-term project and would cost, the estimate at the time was $100 million US, which was a lot of money in those times. But Fermi and Urey had a colleague named John Dunning who tried the same thing that Franz Simon had tried in Birmingham, which was to try to use a sieve for diffusion. And he was able, again, by using a very fine copper sheet, to actually separate a little bit of U-235. And he estimated it would take about 5,000 of these sheets in a serious diffusion plant. Compton then left New York, went down to Princeton, where he talked with Eugene Wigner. And Wigner explained the fast and slow neutron process, and he endorsed the idea of Fermi to make a carbon uranium pile. Remember, the serious problem is, are there enough neutrons to maintain a chain reaction? If you know that, then you can build a bomb. So you don't build a bomb first by separating things. You have to see whether or not it's worth it. And that's why the pile was built. Wigner, of course, knew the situation in Germany very well, and he virtually begged Compton to get moving. Glenn Seaborg went to Chicago when Compton was back and told him he was confident that he could chemically separate out plutonium from other elements because it's a different element and it has a different chemistry. And if you can make enough plutonium, he would be able to separate it. Compton called for yet another meeting on the 21st of October in '41. In Chicago. Lawrence, who was coming from California, asked if he could bring Robert Oppenheimer along. Oppenheimer, of course, was a theorist on whom Lawrence very often depended. At this meeting, the Maud Committee report was read out, and Compton discussed his recent travels and his meetings with Wigner and Fermi and Seaborg, etc. Oppenheimer said he too had calculated the critical mass, and he too agreed that the most conservative number was under 100 kilos. In Germany, Heisenberg was working in Leipzig when he received his first 350 liters of heavy water from Norway. He was now convinced that a bomb was a real possibility. And it was then, in a state of concern, that he made a fateful trip to Copenhagen to discuss the situation with Niels Bohr. And of course, this encounter was the center of the phenomenal play Copenhagen by Michael Frayn, which some of you, I've seen about 4 times. Because it's really interesting. It has only 3 characters, Niels and Margareta Bohr and Werner Heisenberg. It's of course fictitious, but it was a real meeting. Now, Bohr had returned from the US recently, and he was quite convinced that separating isotopes was out of the question, and therefore a bomb was impossible. But Heisenberg apparently asked him, was it right for a physicist to work on a weapons project? Bohr, of course, instantly knew what he was talking about and received a terrible fright, because while he believed that a bomb was impossible, he thought perhaps the Germans had made some great breakthrough and they were working full speed ahead. On the other hand, his reaction, which was very powerful, seems to have convinced Heisenberg that he had learned something in America that was something the Germans did not know, and that the Americans were well on their way to the bomb. So both men seem to have reached roughly incorrect conclusions, and Heisenberg was very unhappy about the visit. There has been, of course, 50 years after the war, there became a lot of revisionist history about what had happened. And recently there have been some discussions that maybe Heisenberg on purpose slowed down work on the bomb. From what I have read and people I've talked to, that's not correct, but who knows. Rudy Pyros, whom I talked about yesterday, wrote the following, that Heisenberg had agreed to sup with the devil and found perhaps that there was not a long enough spoon. It's a famous quote. Compton wrote a report that the word superlative is peculiar. Hardly less than 2 kilograms nor greater than 100 kilograms. Harold Urey was given the job of separating isotopes at Columbia. Lawrence was asked to pursue the problem of electromagnetic separation at Berkeley using his cyclotron. Compton traveled to Washington to meet with Bush and Conant. He added that the element 94, plutonium, should be considered as well. With so many busy people on these committees, this meeting was held on Saturday, the 6th of December, 1941. The next day, the 7th of December, 1941, of course, the Japanese bombed Pearl Harbor. The United States was in the war. Fermi had decided to build a pile using slow neutrons with unseparated uranium-238 because there's a small amount of 235 in that, 0.7%, and that could react with the incoming neutrons, and you could see how many neutrons would come out of that fission. And if it was greater than 1, then you could make a bomb. So that was the project that then was asked. Now, no one really knew what would correspond to what would constitute a critical mass. Fermi calculated that he would need 30 tons of graphite and 8 tons of uranium oxide. The crucial factor is mathematics. I'm sorry, there's one formula here, but I like this formula. So the crucial factor is this number K. K is the number of neutrons released per fission. It is in fact 2.3. Notice if it's less than 1, this is the square root of a negative number, which is not real. Okay? So it has to be greater than 1. M is the distance a fast neutron travels before it slows down enough to get captured. And so the question was measuring this number. Compton's domain now stretched from Berkeley to Chicago to New York to Washington, etc., to Princeton, and that's not a sustainable situation. People needed to be together, they needed to talk. And secrecy had to be maintained, which is hard over distance, and people then generated all these crazy acronym. Plutonium was called copper, U-235 magnesium, and the British called everything tube alloys, all these acronyms. And Compton created a schedule that as follows. Copper in usable quantities by the end of December. This is not far wrong. Okay? We'll see that there were delays to this, and of course the bomb was not ready until the middle of 45, long after the war with Germany had ended. But it quickly became apparent that having spread out all over the country was useless, and so Compton made the decision that everything was going to be done at Chicago, and everybody had to move to Chicago. Fermi, of course, agreed right away. Mrs. Fermi was not so happy because she had a lovely house in a lovely suburb in New Jersey and wasn't so happy to move to a city where it can get quite cold. And the Fermis in particular, I mean, the U.S. was now at war with Italy, and Fermi was an Italian citizen. He was therefore technically an enemy alien. Nonetheless, he was in charge because he was indispensable. Germany, meanwhile, was busily taking advantage of its 2-year head start on the United States. However, the winter of 41-42, when the Germans were in Russia, marked a turning point. Hitler, for example, was learning what the word winter meant in Russia. His troops were not well equipped for -35 temperatures, whereas the Russian troops, who largely were these poor souls out of Siberia, were better clothed and better fed and quite used to horrible weather. The strictures of war on the Nazi regime led them to make any possible research that they were doing or any industrial effort something that was critical to the war effort, not something that might have an effect. And that mattered. Because that put a little bit of a damper on the German nuclear research effort, Heisenberg called the meeting to try to raise the priority. And to this meeting in the February 1942, so this is an early time, he invited the very top Nazis to come to a discussion: Goering, Himmler, Bormann, Keitel, Speer. But in one of the great errors of history that change the future, like the want of a nail in the horse of a shoe, etc., he sent whoever sent out the agenda sent the wrong agenda to all these big shots. And it was a list of very technical papers to be presented, and all these guys had an excuse to be somewhere else. And that situation did not get corrected until June, so they lost 4 months. Okay? But in June, they had such a meeting, and Heisenberg told Speer that a bomb was possible, but there was a lot of industrial problems with separating isotopes and making it work. Speer apparently told Hitler, and Hitler said, "We can't afford to do that," and that was basically the end of the German effort to build a bomb. Its priority was well reduced. That news never reached the U.S. In the U.S., on the other hand, Roosevelt said of this project, it should be pushed, not only with regard to development, but also with due regard to time. Time is very much of the essence. So that time rather than money became the limiting factor. Glenn Seaborg had come to Chicago, and he was given the job of producing plutonium. And he had lots of cyclotrons around the country, all of Ernest Rutherford's, the one in Chicago, there was one in Boston or in Harvard. And he could bombard neutrons with particles from these cyclotrons. From 300 pounds of uranium, he made a microscopic speck of plutonium just barely visible to the human eye. That plutonium is not made that way. Plutonium is now made in reactors, and there is an unfortunate amount of plutonium on this planet. I mean, hundreds of tons of that material. Oppenheimer gathered a group of theoretical physicists to Berkeley for a summer 1942 workshop. And they were quickly convinced that constructing a nuclear bomb was a straightforward problem. Obvious. It's obviously going to work. Physicists love that term. What attracted them instead, particularly Teller, was the question of the fusion bomb, now something we call the hydrogen bomb, which Teller called the super. They knew that the ordinary bomb, bad enough, needed experiments rather than theoretical work. And they all believed that the Germans, with their head start, were working at full speed on this. By June 42, Bush proposed to Roosevelt that the Army Corps of Engineers be brought in to build the plants necessary for the industrial efforts. And this project, which had begun with a bunch of scientists sitting around talking, now was in the hands of the military, and that's a very different organization. The Army Corps of Engineers had a man in mind. His name is Leslie Groves, and he had had a previous job of building the Pentagon. This job of building the bomb was small, by the way, compared to building the Pentagon. He's been described by compatriots as a lone wolf, and in these words, the biggest son of a bitch I've ever met in my life, but also one of the most capable. He had an ego second to none. He had tireless energy. He was a big man. We would use the word fat today. He was about 120 kilograms. A heavy man, but he never seemed to tire. The Army Office of Engineers originally, when he started the project, was in Manhattan in New York, and that's why the project was called the Manhattan Project. There is you can see things are getting, there's the president, there's Henry Stimson, there's Groves. You can see how many people are involved. This is later on, after, this is already May 1945. But there were a lot of people involved. It was a very serious project. Groves discovered that a rich source of pitchblende, which is the ore which contains uranium oxide, had been shipped to the U.S. from the Belgian Congo in 1940, and it was done, of course, to keep it out of the hands of the Nazis, and this even before their invasion of Belgium. There were 1,250 tons of ore sitting in barrels on docks in New York, which he quickly bought. He also bought 52,000 acres of land along the Clinch River in eastern Tennessee, an area soon to be called Oak Ridge. Now, working with dangerous chemicals and with radioactive materials is a very serious and hazardous business, and there were accidents. For example, powdered heavy metals are known to be very dangerous. They can, in contact with air, they can catch fire. Okay? And this happened to Walter Zinn at Columbia, a famous Columbia physicist. He opened a can of thorium, which is element 90 in the periodic table, and it immediately ignited. Now, he knew that this was dangerous, so he had goggles and gloves and a rubber apron. Nonetheless, the goggles saved his eyes, but he was badly burned, and he took several months for him to recover. Worse than that was a combination of radium and ground radium and beryllium powder, which is a neutron source that was commonly used. And the radium, of course, gives off alpha particles. The alpha particles hit the beryllium atoms and knock a neutron out. Fermi and his student Herbert Anderson were heating this mixture to get this powder, to get the moisture out of it. And they put it on a hot plate in a room. They were outside, and when they peeked in, the room was filled with smoke. And so they rushed in, turned the thing off, the hot plate off, rushed back out, and several years later, Anderson was diagnosed with a very rare disease called berylliosis, which was due to the deposit of beryllium atoms in his lungs. He had to have a lung removed, and he had trouble breathing and walking for the rest of his life. I knew him in Chicago in 1966 and 67, and he was in very bad shape. Even worse was the cancer that killed Enrico Fermi in 1954, and lots of other physicists who had worked with radiation in the early days. Starting in May 42, Fermi and co-workers began building a pile in the squash court under the stands at Stagg Field at the University of Chicago. Stagg Field is the former football stadium of the university, and I worked there at the university 25 years later. And I had great respect for the University of Chicago because it is the only place in the United States of America where they tore down a football stadium to build a library. I thought that was a tremendously positive event. Generally, at every university in the US, the football coach is paid 10 times the salary of any professor. Sometimes more than 10 times. The arrangement was called CP1 for Chicago Pile Number 1. It was enormously secret, and no one was allowed to discuss it with family or friends or wives when they got home, except for Leona Wood, who was not allowed to discuss it with her husband because she was the only woman then working on the project. Fermi was particularly watched as an enemy alien. The FBI was all over the place, and they were nuts. And for example, his post was opened, and he was not allowed a shortwave radio, which he loved because it allowed him to get news broadcasts from Europe. So, now, he wanted to build the pile in the shape of a sphere, using layers of graphite with holes in it into which spheres of uranium would be placed. The uranium fissions. It emits a neutron of high energy or fast neutron, but then this neutron bounces off carbon atoms and slows down, losing energy in each collision until it gets captured by another nucleus, the uranium nucleus, and then emits, he hoped, more than one neutron. That's what he was trying to find. And of course, as I mentioned, pure graphite was necessary. The purer, the better, to get rid of the boron contamination, which is normal in normal graphite, and boron is a big eater up of, or capturer of neutrons. The shape of a pile as a sphere meant that the lower half, of course, had to be supported, and lots of wood was also necessary. Air was a problem because air also absorbs neutrons. And so Fermi originally thought of pumping all the air out of the room. But then everybody would have to work in a diver's suit, and that was not possible. And so Herbert Anderson was able to go to a big tire manufacturer and get a rubber bag 6 meters on a side to surround the entire thing. By September of 42, large quantities of very pure graphite were arriving, as well as 30 tons of uranium oxide ore a month. The Manhattan Project was the highest priority work in the United States. Ore had to be, which was a powder, had to be compressed into spheres, and they had a big heavy-duty press to do that. But the real problem is in this graphite, because it's black, greasy, heavy, and it had to be machined down into very smooth surfaces so it fit as well as possible, and logs had to be made out of it. And then semi-spherical holes had to be put in so that the sphere could be dropped in and then another one come on top. Moreover, slots were put in for cadmium control rods, because cadmium is very, very good at swallowing up neutrons, and so if there was a problem, you could put a cadmium rod in, and that would stop the reaction because it would kill all the neutrons. There is a scale picture of CP1. It's a big device. There is a human being. These are graduate students at the top, of course. Groves showed up in October of 42, pushed very hard for results, and then left for Berkeley to see what was going on with the plutonium work. Now, he had also bought land in Hanford, Washington. Hanford being an isolated little village close to the Columbia River, so he had lots of water, and close to the Grand Coulee Dam, so there was lots of electricity, and they were building piles there to make plutonium, which is what actually supplied that. And so he had convinced the DuPont company to take over the running of the plant. And DuPont didn't want to do that, but eventually they agreed under the condition that they would be paid $1, because they did not want to look as a company that made a profit from war work. How much the world has changed these days. By mid-November, Fermi had 2 12-hour crews a day crew under Walter Zinn, a night crew under Herb Anderson, and they managed 2 layers per shift. As construction, he had predicted that he needed 76 layers, but as construction proceeded, they got purer and purer graphite, so he was able to get rid of the rubber bag and reduce the number of layers necessary. And he calculated that somewhere around layer 56 to 57, the magic number K would be greater than 1. And that meant a sustaining reaction would just become possible. He also collapsed the sphere, making it somewhat ellipsoidal. The crew reached 57 layers on the 1st of December, 1942. Anderson, in accordance with an agreement with Fermi, removed all the cadmium rods. They had cadmium rods that they put in and locked, and only Zinn and Anderson had the keys to take them out. But at this time, on the 1st, he took them all out, except one, and he measured the neutron count, and it became completely obvious that this thing taking that last one out, would make the reactor go critical, that is, greater than 1. So they stopped work, they put them all back, put all the locks back in, and that was the end. The pile then had 350,000 kilos of graphite, 37,000 kilos of uranium oxide, and almost 6,000 kilos of pure uranium metal. All the uranium, of course, was natural uranium, so that there was only 0.7% of really fissionable things. The reactor was not a power generating reactor. It would generate about 0.5 watt of electricity, not enough to light a light bulb, of course. In normal reactors today, they make a lot of heat. The heat is taken off by like a coal-fired power plant or a gas-fired power plant, which heats a liquid. The liquid is taken off. It's blown against a turbine to turn a turbine wheel. That turns a generator. In turn, that generates electricity. So it's just a means of making basically hot water. After each day's construction, Fermi compared the results, the neutron rate, with his calculation to make sure he understood what was happening. He calculated it using a machine, the calculator of the day, which the young people in this room will never have seen, probably. This is a calculator. It's an analog calculator, not a digital calculator. It's called a slide rule because it slides. This was mine, bought when I was about 14, so it's very old. And it's wonderful. I still use it on rare occasion. I've showed my kids how to use one of those. They've never seen one, of course. Now, the morning of the 2nd of December in Chicago was very cold. The temperature was minus 18 degrees, and I have been in Chicago in days like that. The State Department on that day announced that over 2 million Jews had been murdered so far. 5 million more were in severe danger. The Americans had landed troops in Algeria. Montgomery was fighting in Egypt. Rommel was planning counterattacks on both directions. The U.S. Marines were fighting the first of bloody battles, island battles on Guadalcanal. And in Chicago, Fermi was getting ready. He was not only a brilliant physicist, but he was a hell of a showman as well. He had arranged for the neutron counter to be hooked up to a device that clicked, so you could hear the click, click, click as the neutrons were there. He also had a balcony in which most people, the big shots, were all staying, and he had a chart recorder showing the neutron rate as it increased and increased. He took lots of precautions. Not only did he have all these cadmium rods, but he had 2 zip rods that were cadmium, one with an electric switch to drop, one tied with a rope, and he had a graduate student on top with an axe to cut the rope. He had 3 graduate students on top with big buckets of cadmium sulfide to pour over the pile if necessary. All rubbish, because he knew it was going to work. So he ordered all the rods pulled out except one, and he checked the numbers for the night before. And he then said, take the last rod out 4 centimeters. Okay? And they did that, and he did all those calculations with his little machine. And the neutron count every time went up and then stopped and leveled off. At 11:30, he was ready. He said, I'm hungry, it's time for lunch. So all the rods were put back in and locked, and everybody went off for lunch. And they came back at 2:30 and repeated, took all the rods out, and then at the crucial moment came, he told Walter Zinn, who was on top, pull the last rod out 30 more centimeters. And he announced to people that this will do it, that the chart recorder will not level off, it'll just keep going up. The pile will be critical. The number K will exceed 1. The clicking, of course, became a roar as the count rate went up. And so they was eventually switched off, and the chart recorder was banging up against the top, so the scale had to be changed all the time. He waited about 2.5 minutes and then said, put back all the zip rods. And the pile stopped, of course. The controlled release of atomic energy had, in fact, been achieved, and the world was a different place. Eugene Wigner, who was there, wrote of his emotions at the time. For a long time that we would unlock a giant, but now we had actually done it. We felt that we had done something which we knew would have far-reaching consequences, but we could not foresee what they would be. He managed to find a bottle of Italian Chianti, which was very rare because you couldn't import anything from Italy. And Al Wattenberg, a physicist I knew from Illinois, had it signed by everybody. There's Walter Zinn, there's Enrico Fermi. Everybody there signed the bottle. This is in some famous museum now, I'm not sure where. Compton, who was there, called James Conant in Washington and recorded the conversation. He said, Jim, you'll be interested to know that, I have the words here on the slide. You'll be interested to know that the Italian navigator landed in the New World. The Earth was not as large as estimated. In other words, the pile had 57 layers, and he arrived sooner than he expected. Were the natives friendly? It worked, okay? On the 2nd of December in 1967 was the 25th anniversary of this event, and there was a ceremony at the University of Chicago. A statue by Henry Moore was unveiled by Laura Fermi, who was then Enrico's widow. He had died in '54 at the age of 53 years old. And these days, when help for terminally ill patients is openly discussed, Fermi was really famous for asking why the hell he had to suffer so much. He said, they treat dogs better than they treat me. The statue is a very brutal reminder, I think, of what nuclear weapons can in fact do. There were lots of veterans of the Manhattan Project there, and a lot of Nobel laureates and a lot of distinguished physicists, and pieces of the original carbon block were cut up, encased in plastic, and distributed to all of them. But there were pieces left over, and I was a young postdoc at the university and friends with the secretaries, so I got a piece. And it's one of my most treasured possessions. It says, graphite from CP1, the first nuclear reactor, December 2, 1942, Stagg Field, the University of Chicago. I'm going to put this away so nobody can swipe it. I mostly got that because Glenn Seaborg, who was a Swedish immigrant, heard me talking to my year-and-a-half-old daughter at the time, and we raised her in Swedish, and so I was speaking Swedish to her, and Seaborg overheard, and so that's where I got. Okay. What bothered Groves was that all the work that had gone on was theoretical. It was, yes, this works, yes, we can do this, yes, etc. Lots of talk. But everybody was telling Groves, it's just a matter of detail in a few months. But he was a very practical guy, and he did not put much faith in that. Of theory, there was a great deal, he said. Of practical anything, proven knowledge, there's nothing. He was worried about making a bomb, something that would actually go off and actually fit in an airplane. The actual bomb was called in those days Project Y, and he was looking first for somebody to run Project Y, and secondly for a place to put it. And Oppenheimer's group at Berkeley had been able to make all these guesses about bomb yields, but not on detonation or size or anything. Groves couldn't think of anybody better qualified than Oppenheimer to run the project. And he wanted him. But there were security problems with Oppenheimer, and they never went away, but he wanted them in any case. And I want to just talk about Robert Oppenheimer for a few minutes. He had a very youthful appearance, and he was an extremely sensitive man. He was a chain smoker, something which eventually helped kill him. He drank too much, he ate too little. He took a great delight in highly spiced foods, which made his dinner companions generally very unhappy. He was considered dashing and by some women rather handsome. He certainly was extremely chivalrous and attentive. Men could either be amused or antagonized by him, depending. He was considered the fastest thinker of anyone around and had an iron memory. But he also had a tendency to make people feel stupid or foolish. So that really brilliant people like Hans Bethe, who was the head of the theory group at Los Alamos and was very much the equal of Oppenheimer, just was amused by him. Ernest Lawrence, who was considered by Oppenheimer just an ordinary experimentalist, was greatly insulted, but he needed Oppenheimer, and so he tolerated him. Oppenheimer knew of these faults, he didn't change them. In the 1930s, both of Oppenheimer's parents had died, and before this had happened, he was largely divorced from contemporary events, even in the 30s. He read widely classics, poetry, plays, along with other parts of science. He studied and could read Sanskrit, and he spoke most European languages. But he was unaware of the Great Depression, he was unaware of economics, and all this began to change in 1936. He had Jewish relatives in Germany, and they were in danger. He managed to get them out, but he certainly became aware of the fate of people there. He also became aware of economics because he had a lot of really brilliant students, but he couldn't find jobs for them because there weren't any jobs. So he understood that politics and economics could affect people's lives, and this made him get interested particularly in left-wing politics. And so he became deeply involved with a young woman named Jean Tatlock, who was a member of the Communist Party of the United States, and they came very close to getting married. And she introduced him to all these people of very left-wing basis. But then he met Catherine Pining, Kitty, as she was called, in 1939, a woman he would eventually marry. She had been previously married 3 times. The second time to Joe Dallatt, who was the secretary of the American Communist Party, and he had been killed in 1937 fighting in Spain. But by 1939, she was terribly disillusioned with communism. The word of the Stalinist purges was getting out and so forth. People were wising up to what Soviet Union was really about. And so with her relationship with Oppenheimer, she weaned him away from his left-wing friends. Groves considered Oppenheimer a true genius. He found only one subject on which Oppenheimer was not an expert and could not discourse, and that was sport. So Grove made his personal decision already by the mid-October of 42, before the pile was done, and he overrode all the security. I mean, he was a tough guy.